Usually when we talk about starting a brand new project, there is this, I don't know, this universal feeling of dread that comes with the blank page.
Oh, absolutely. The blinking cursor.
Right, the blinking cursor. It's like standing at the edge of this really dense, completely unmapped forest. You have to figure out where to place the first stone, how to clear the brush, where the water lines will go,
Yeah.
and just exhausting before you've even built a single thing of value.
Well, the initial friction of setup is, I mean, it's arguably the biggest drain on productivity we have. We tend to romanticize starting from scratch as this, ultimate act of pure creation.
Right, like the genius at work.
Exactly. But the reality of staring at a blank page is that it is often incredibly inefficient, especially when you are building complex systems where the underlying mechanics, they don't actually need to be reinvented every single time.
And that friction, that exact feeling, is what we are tackling today. So our mission for this deep dive is to give anyone listening, whether you are, managing software, running a business, or just trying to organize your own daily workflow, a framework for building complex things efficiently. We are exploring the philosophy and the hard data behind a completely different way to work. And this is based on two really fascinating sources from researcher Maurizio Rizzari.
Yeah, these are great sources.
We've got a LinkedIn article from August 24th, 2026, which details the development of what are called syrag-template modules,
Right.
and a Zenodo case study from May 2026 that tracks the evolution of these modules in the real world. So we're looking at the theory and the practice.
Yeah, and the overarching goal here is to understand how standardizing the structure of our work rather than the content itself can lead to these massive leaps in both speed and quality.
Right.
And crucially, how to achieve that velocity without just handing the keys entirely over to artificial intelligence and, hoping for the best.
Because that is the temptation right now, right? Just letting the machine do all the heavy lifting.
Oh, for sure.
But before we even get to the artificial intelligence aspect, okay, let's unpack this.
Yeah.
We need to understand the architectural foundation Rizzari is talking about. In his work, every new syrag module, which is basically a discrete piece of software functioning within this larger ecosystem, it starts with a foundation called the syrag-template-manager.
Right.
Now, on its face, a template manager sounds like, I don't know, a basic shortcut, like a Word document template.
Yeah, like a resume template or something.
Exactly. But the research is very careful to clarify what this manager does and what it does not do.
Yeah, it is explicitly stated that this template manager does not automatically generate a complete application.
Okay.
It doesn't do the high-level thinking for you, and it certainly doesn't replace the work of a person who actually understands the specific, nuanced problem that the software needs to solve.
So if it's not writing the application for you, what is it actually doing under the hood?
Well, according to the source, it locks down conventions.
Okay.
We're talking about those repetitive, tedious decisions that drain your energy at the start of a project.
Like the brush clearing we talked about earlier.
Yeah, exactly. It decides how to organize the file folders, how to describe the module to the rest of the system, how to launch it,
Okay.
even how to expose state control, meaning how the software keeps track of what it's currently doing. It manages the configuration, the diagnostic logs, the local data storage. It creates what Rizzari calls a deterministic structure.
A deterministic structure. Okay, I want to pause on that
Sure.
because that terminology feels essential to grasp.
It is. The article notes that this structure is deterministic not because every single aspect of the final product is decided in advance.
Right?
It's deterministic because the elements that shouldn't be reinvented are made completely stable and predictable.
You aren't wasting cognitive load on the plumbing.
Yes. You know exactly where the pipes are, how the water flows, and where the shutoff valves are located.
But I do want to push back on that idea of locking down the structure, though.
Okay, let's hear it.
If a structure is strictly deterministic, and all the files, the configurations, the logging mechanisms, if they all have to follow this exact same rigid skeleton, doesn't that inherently make the resulting software rigid?
Well, no, because...
I mean, if every application has to use the exact same foundational blueprint, it seems like you just end up with a system full of identical, inflexible clones.
Right. I see what you're saying, but what's fascinating here is that the standardization only concerns how the module exists within the broader operating environment, not what it actually does.
Oh, I see.
Yeah, the article makes a very sharp distinction here between operational mechanics and domain logic.
Operational mechanics and domain logic.
Exactly. The shared structure doesn't serve to make the modules identical in purpose. The specific logic, the domain content, the data processing rules, all of that remains entirely free to evolve based on whatever the client requests or the designer envisions.
Okay, let me see if I can translate that into a physical analogy. Go for it.
It shaves like standardizing the electrical grid of a city. The voltage, the frequency, the shape of the wall outlets.
Yeah.
That is all highly deterministic and rigid. It's identical everywhere. But what you actually plug into that wall outlet, a toaster, a supercomputer, a desk lamp, that's entirely up to you.
That is a highly accurate way to
Well,
visualize it.
the grid doesn't care what the appliance does as long as it speaks the same electrical language.
Exactly.
Mm-hmm.
The Syrag platform provides a common language for describing the module, launching it, monitoring its status, connecting it to other components in the ecosystem. But the domain content itself, the toaster or the supercomputer,
Right.
it's insulated from that standardization. And this separation is the genius of the approach. By locking down the operational mechanics, you leave the specific application logic completely unconstrained.
Wow, okay.
It allows a common technical framework to support applications designed for vastly different needs without restricting their specific requirements. Which naturally leads to the next phase of the process.
Yeah.
If the municipal grid is laid down and the foundation is poured, who is actually putting up the walls and designing the rooms?
Right.
Because we live in an era where the immediate assumption is that automation means removing the human entirely from the loop. Like, is an AI just running the show from here on out?
The SaaSware ecosystem explicitly pushes against that assumption.
Really?
Yeah. The process works through a mechanism called the syrag module generation skill. So when a new module is needed, a request comes in defining its name, its interface, its layout, its purpose.
Okay.
From there, the model manager generates that deterministic foundational skeleton we just discussed.
So the skeleton is generated. But the article points out that from that exact moment, the work shifts into active testing and development.
Yes.
The module is launched in its environment, its baseline responses are checked, and then comes the heavy lifting, creating and validating the actual application logic. This is where the human and the machine have to interact.
And in this phase, the role of artificial intelligence is very clearly defined, and more importantly, it's strictly bounded.
Bounded how?
Well, the AI acts as an incredibly fast support mechanism.
Yeah.
It can help propose ideas, it can draft texts, it can even write out drafts of specific functionality based on prompts.
Sure.
But the source material is adamant about what the AI does not do.
Right.
It does not independently determine the overarching model to use. It does not certify the domain logic. And it absolutely does not publish the module without the explicit decision of a human operator.
Okay, but let's look at the psychological reality of how humans interact with these tools, though.
Okay.
With AI doing so much of the upfront work, drafting the text, proposing the ideas, generating the structural skeletons, aren't humans in danger of just becoming passive rubber stampers?
That's the fear, right?
I mean, it's easy to say the human is in control, but if a machine hands you a 90% finished product, human nature dictates that a lot of people will just skim it and click approve to save time.
And this raises an important question, right? That tension between speed and accountability is one of the most critical challenges in modern software development.
Yeah.
But the article addresses this directly with a pretty profound statement. It says, speed of support does not eliminate process responsibility.
Speed of support does not eliminate process responsibility.
Right. In the system, the human isn't just a passive observer waiting in the end of an assembly line. The human is the ultimate validator.
Meaning the accountability rests solely on the human shoulders.
Mm-hmm.
If the software calculates something wrong, you can't just throw your hands up and blame the language model.
Exactly. The system's entire philosophy dictates that the AI is fundamentally incapable of certifying anything.
Wow.
AI provides the velocity, right? It generates the raw material quickly. But the human provides the certification of the domain logic.
So to use your earlier analogy,
The electrical grid.
right, the AI might sketch out the wiring diagram for the supercomputer you want to plug into the wall, but a human engineer has to certify that the diagram won't cause the machine to catch fire.
Yes. It's a hybrid mode where you capture the speed of artificial intelligence, but you maintain the critical thinking and the liability of a human expert.
Now, philosophy and theory are great, but, anyone can write a white paper about how software should be built.
Fair enough.
The real question is whether this hybrid, structurally standardized approach actually holds up under real-world pressure.
Right.
And here's where it gets really interesting. That is where the Zenodo case study from May 2026 becomes incredibly valuable because it provides empirical weight to all this theory.
Yeah, the comparative evolution analysis in that study is revealing. So it looks at two different software modules built on this exact shared infrastructure to see how the development process actually played out.
Okay.
First, it analyzes the Syrag lab core, which was their foundational project.
Right.
The data shows it went through 10 iterations and achieved a base coherence, often denoted as CON, of 0.42.
Okay, let's pause and define that metric because to anyone outside of systems engineering, a base coherence of 0.42 doesn't mean much.
I know, it sounds like jargon.
Yeah, what exactly is CN measuring in this context?
So base coherence, or CN, essentially measures the structural stability and integration maturity of a system.
Okay.
It evaluates how well the various components, the user interface, the database connections, the logic processing, how well they hold together without fracturing under stress.
Okay, so it's a measure of stability.
Yes, and a coherence of 0.42 was the established baseline for the core lab after 10 development cycles.
10 cycles, 0.42. Got it.
Then the study compares that to a derivative project called the sensor lab.
And the sensor lab started from a slightly lower base coherence of 0.35, which implies it had, a bit more initial ambiguity or complexity to sort out, right?
Exactly. It started from a harder place. Yet despite that lower starting point, the sensor lab reached a comparable level of maturity in just 4 iterations.
Wait, 4? Compared to 10?
Yes. That is 60% fewer iterations than the core lab. In practical terms, they achieved a 2.5 times speed-up in development velocity.
Okay, to put that in perspective, think about a successful chef who decides to open a second restaurant.
Oh, I like this.
When they opened their first location, they had to figure out everything from scratch.
Yeah.
The supply chain for ingredients, the layout of the kitchen stations, how to handle reservations.
The operational mechanics.
Exactly. And let's say it took them 10 chaotic months to get it running smoothly.
Right.
But when they open the second location, they already have the supply chain perfected. The kitchen layout is standardized. They can skip all of that trial and error and focus entirely on designing the new menu.
Yeah.
So they reach opening night 2.5 times faster. But here is my concern with that. Moving that fast usually means breaking things. When you accelerate development by 2.5 times, aren't you inevitably introducing more errors?
You'd think so, right? The conventional wisdom certainly says that speed sacrifices stability. But the Zenodo data proves the exact opposite happened here. Not only did the sensor lab reach maturity 2.5 times faster, but the team also resolved 1.7 times more bugs per cycle.
Wait, how does that mechanically work? How do you move 2.5 times faster while simultaneously increasing your capacity to find and fix bugs?
It comes back to the deterministic structure and the reuse of established components. The acceleration didn't happen because the developers suddenly started typing faster.
Right.
It happened because the sensor lab didn't have to invent its foundational mechanics. The study specifically notes that they reused a debugged associator engine.
An associator engine being the mechanism that links different data points together, right? Like associating a specific temperature reading from a sensor with a specific timestamp.
Correct. And
Yep.
since the Sawag core lab had already spent countless hours testing and debugging that exact associator engine, the sensor lab team could just plug it in.
Oh, wow.
Yeah. They also reused the report pipeline, the API patterns, the overall quality control philosophy.
So the nature of the bugs they were fixing completely changed.
Exactly.
They weren't wasting time figuring out why the application was crashing on startup or why the logs weren't saving properly. Those foundational structural bugs were already eliminated.
Gone.
So when bugs did arise in the sensor lab, they were high-level logic bugs specific to the new sensors.
Yes.
And because their cognitive load wasn't drained by fixing the plumbing, they had the mental bandwidth to identify and resolve those complex logic bugs much more efficiently.
That's it exactly. And the case study quantifies this phenomenon as the standing on shoulders effect in relational software evolution.
Standing on shoulders.
Yeah. When you reuse a debugged engine, you are literally standing on the shoulders of your previous perfected work. You aren't making beginner mistakes twice, which elevates the entire baseline of your new project.
So we have the theory of the deterministic structure. We have the data showing a massive speed up and higher bug resolution. But what does this pipeline actually produce out in the wild? The article mentions that this exact foundation, the syrag platform and the template manager, it gave birth to some highly varied modules. We are talking about the syrag-template-manager, the syrag EU funder, the syrag patent manager, and the syrag copyright office.
Which is wild because these are application domains that seem completely unrelated on the surface.
Right. I mean, managing value-added tax involves complex financial algorithms and localized tax codes.
Yeah.
But managing copyright law or European Union funding involves intellectual property registries and bureaucratic compliance.
Totally different worlds.
So how does the exact same template manager run a tax calculator and a copyright office?
Because of how cleanly the system separates the how from the what.
Right.
Think about the underlying actions required by both applications. Whether a user encounters an error while calculating a tax rate or while uploading a copyright manuscript, that error needs to be logged into a diagnostic file. Both applications need a way to authenticate users securely. Both applications need an API to pull records from a secure database.
I see.
The syrag-template-manager handles the error logging, the user authentication, and the database routing identically in both modules.
Wow.
The domain logic, the actual math for the tax, or the validation rules for the copyright is the only unique code the developers had to focus on.
So by providing established conventions, tools, and knowledge for the operational mechanics, wildly different modules can be brought to market faster and with higher stability.
Exactly. The system supports manual coding, it supports LLM generation or hybrid modes. But the ultimate goal remains the same: transforming previous work into a better foundation for the next project, constantly reducing that initial ambiguity.
And the broader implications of this approach, I mean, they extend far beyond software engineering.
Oh, without a doubt.
So what does this all mean? How would a listener apply this concept of separating structural standardization from domain logic to their own workflows, say preparing for meetings, organizing research, or managing a small business?
If we connect this to the bigger picture, the lesson here is universal for anyone trying to optimize their productivity. Whether you are coding a VAT manager or prepping for a weekly marketing sync, you likely waste an enormous amount of energy on setup.
The fiction of the blank page again?
Exactly. But if you build a deterministic structure for your own life, you eliminate that friction.
You build your own syrag-template-manager for your daily tasks.
Exactly that. You create a rigid template for your meeting notes so you never have to think about how to format them again.
Right.
You establish a standard folder structure for your digital files or a standardized checklist for onboarding a new client. You lock down the predictable operational elements of your workflow.
Yeah, you standardize the how so you can put all your genius into the what.
Yes. By doing that, you free up all of your precious brain power to focus on the real problem, the domain logic.
You stop reinventing the shape of the brick every Monday morning. You ensure that every time you sit down to work, you are standing on the shoulders of your past self.
It fundamentally changes your relationship with your work. You are no longer fighting the environment. You are just executing the task.
That is an incredibly practical takeaway. We've covered a lot of ground today. We started by looking at how standardizing structure, file organizations, the APIs, the logging mechanics, how that eliminates the blank page problem without making the final product rigid.
Right.
We saw how keeping human accountability firmly in the loop ensures that the speed of AI doesn't compromise the validity of the domain logic.
Mm-hmm.
And we unpacked the Zenodo case study, which proved that reusing debugged engines results in massive leaps in efficiency, a 2.5 times speed up, and resolving 1.7 times more bugs per cycle.
It serves as a masterclass in relational evolution and building complex systems sustainably. But before we conclude our analysis, there is one final unexplored detail from the source material that demands attention.
Oh.
It's a tiny note at the very bottom of the LinkedIn article.
I think I know what you're talking about.
It is easy to miss, but its implications for the future of this technology are staggering.
I noticed that note as well, the one tucked away with the little information icon.
Yes. It states, and I quote, "All SYR content is generated by LLMs that directly scan existing software."
Wow.
Yeah.
When you really pause to think about the mechanics of that statement, it shifts the entire conversation.
It really does.
Yep.
Because we've been discussing how this ecosystem uses a deterministic structure to help human developers build faster.
Right.
But if this system relies on large language models that are actively and directly scanning its own existing structurally perfect modules to learn how to build the next ones, are we looking at the dawn of a completely self-replicating cycle of optimization?
If the AI is learning to build the next module by scanning the structural perfection of the previous module, it is essentially teaching itself using its own optimized past.
Where is the ceiling on that 2.5 times speed up? If the LLM is learning from code that has already resolved 1.7 times more bugs, the foundational knowledge base gets purer with every single iteration.
Does that 2.5 times speed up eventually become 5 times? Or 10 times?
Right.
That is a wild concept to end on. If the blueprint is constantly reading its own best, most debugged versions to generate the next blueprint, that blank page we talked about at the beginning isn't just filled in for you. It's filled in by an expert system that has perfectly memorized every structural success and every resolved bug you've ever had.
It evolves from merely standing on shoulders to building an exponential ladder of efficiency. The human still steers the ship and certifies the destination, but the engine driving them forward becomes incomprehensibly powerful.
What a compelling vision of the future of work. Well, that is a wrap on today's deep dive into the architecture of efficiency. We hope this conversation gives you some powerful new ways to structure your own projects, separate your plumbing from your domain logic, and finally, skip that dreaded blank page. Keep digging into these concepts, keep building your own deterministic structures, and, as always, keep learning. Until next time.